Hello and welcome to our video covering section 5.4 of your textbook. In this video, we will discuss the topics of least squares and data fitting. If you are into applied math, this is going to be your jam. All right, let's start with least squares. And actually, let's start with a totally unmotivated trip down memory lane discussing the orthogonal complement again. So, okay, suppose we have some subspace V, and let's have that subspace be the image of A, where A is some matrix with these column vectors. So consider V being the image of A. Well, just by definition of the orthogonal complement of some subspace V is just the set of vectors such that X dotted with V is 0 for every vector V in the subspace capital V. So, okay, that's just definition of orthogonal complement. And then we saw a theorem that said, well, actually, if your vectors, say v1 to vm, span the space, which they do, these span the image of A, which is V in our case, well, then you don't actually have to check that x dotted v equals 0 for every v in V. You can just check that x dot vi is 0 for these basis vectors. And then we saw in a previous video, a recent one, that, well, we can write the dot product of two vectors as a matrix multiplication where we have a 1 by m matrix and an m by 1 matrix. Wait, did I say that right? 1 by m, yeah, I did. Okay, whew. Okay, so what did that get us? Well, this tells us that actually the orthogonal complement of the image of A, this is actually going to be the kernel of the matrix of A transpose. And let's just convince ourselves that that's true for a second. Okay, so A transpose is what you get when you just take A, you take its column vectors, and now you make those columns the rows instead. And so the kernel of the matrix A is the set of vectors X such that, well, when A transpose X equals 0, but A transpose X, when you're doing the row version of matrix multiplication, that's just going to be, this row vector times dotted with X, and then that'll be the first component and of your result. And if that's going to be 0, that means V1 dotted with X had to be 0. Similarly, V2 dotted with X has to be 0 if the second component's going to be 0, and all the way down. So X is in the kernel of this matrix, even only if Vi transpose dot X is equal, Vi dot X or Vi transpose times X is 0 for all of these basis vectors. So there we have it. The orthogonal complement of the image really is the kernel of this matrix. And let's write that down as a theorem. And as we'll see, this is going to be handy later. So let's do an example. And this is just going to be a simple one. So just consider the line that is the span of the column vector 1, 2, 3, or the image of this vector by multiplication of this vector 1, 2, 3. So from Calc 3, we know that the orthogonal complement of the image is the plane with this normal vector. And so I mean, yeah, if you have like a vector, this vector 1, 2, 3, and you want everything that is perpendicular to that vector, that's going to be the plane where this vector is normal. And from Calc 3, we know that this is given by this equation. All right, now let's use our knowledge from linear algebra. From theorem 5.1, the orthogonal complement of the image is going to be the kernel of A transpose, which is the vector, the 1 by 3 matrix 1, 2, 3. And okay, what's the kernel of this? Well, it's the set of x, y, z such that this matrix times x, y, z is the 0 vector. And then matrix multiplication just tells us that indeed this is x plus 2y plus 3z equals 0. So really, this is just to reassure you that this is true by solving it in two ways. One, a way you already knew how, and just confirming, okay, using the theorem, you still get the same thing. Okay, so this is a really useful theorem, but again, totally unmotivated. So here it goes. Here, we'll start with just part A of the theorem. Part A says, if you have some matrix A and it's n by m, so not necessarily square, you have some matrix A, it's n by m, then the kernel of A is equal to the kernel of A transpose times A. And you're like, okay, I guess. So let's prove it, even though we have no idea why we care about something like this. So here's our strategy. First, we're going to show that if some vector x is in the kernel of A, then x must also be in the kernel of A transpose A. And then the next step is we're going to show, well, if x is in the kernel of A transpose A, then x is in the kernel of A. So we're going to do both. Well, if we're doing this first, we assume by x is in the kernel of A. And what does that tell us? Well, by definition of the kernel, that means ax equals 0. And then we're just going to hit this equation on both sides by A transpose. Now, A transpose times the 0 vector is going to be 0. And so we get A transpose A. X is 0, which means that x is in the kernel of A transpose A. So now we want to show if x is in the kernel of A transpose A, then x had to be in the kernel of A. Again, let's start with our hypothesis. Suppose x is in the kernel of A transpose A. What does that mean? Well, by definition of the kernel, this means that A transpose A x is the 0 vector. And this tells us that A of x is in the kernel of A transpose. But then that tells us, by the theorem we just saw, that A of x is in the orthogonal complement of the image of A. So this is retroactively justifying that first unmotivated theorem. So, okay, we have that our string of implications tells us that if x is in the kernel of A transpose A, then AX is in the orthogonal complement of the image of A. But notice AX is also in the image of A, because, okay, any vector, A times that vector, that's going to be in the image of A. And so X is both in the image of A and in the orthogonal complement of the image of A. And as we've already seen, the only vector in the image of A and really the only vector in some subs that is both in a subspace and its orthogonal complement is 0. All right, so that tells us that AX is the 0 vector, and that tells us that X is in the kernel of A. So, okay, we did it. We proved this part A. So now what was part B? Part B says, if A is an n by m matrix, where the kernel of A is 0, then the matrix A transpose A is actually invertible. Let's see why this is true. First, let's notice that A transpose A is actually a square matrix with dimensions m by m. So think about this and think about the dimensions of A, and if A is n by m, then A transpose is m by n. And yeah, if you think about it, okay, this as a transformation takes a vector, an m-dimensional vector, and spits out an m-dimensional vector. So it really you end up with a matrix that is m by m, which is good because square matrices are the only candidates for invertible matrices. All right, and then as we saw in part A, if the kernel of A is 0, then the kernel of A transpose A is 0. But if you're a square matrix and the kernel consists of only the 0 vector, then your matrix is invertible. I forget what theorem that is, but based on your homework, this was everybody's favorite test for invertibility, so I think you know it. Okay, now we're getting to least squares. This is just a super important idea. So it's important enough that I'm actually going to first just talk about the main idea, and then we'll get into the details. So here's the main idea of least squares. Suppose you have some inconsistent system, like ax equals b, but there's no solution x to this. Geometrically, we think of this as, okay, you've got the image of A, and if B is some vector that's not in the image of A, then AX equals B is never going to have a solution because AX is always going to be in the image. Okay. So yeah, no value of X is going to be a solution, but this is a common theme of least squares. Don't give up. So what you do is if in the method of least squares is you look for some vector, we'll call it X star, such that AX star is as close to B as possible. So the idea is, okay, you're not going to be able to solve AX equals B, but can you get close? And how close can you get? So we ask, all right, well, what vector in the image of A is as close to B as possible? And actually, it's the projection. And hopefully this makes sense. I mean, if you want to say this is your vector B and you want to say, all right, well, what's the closest vector in the image? We'll just project down, just do a straight line down immediately. And hopefully you'll see if you drew a line that wasn't straight down, something like this, then this line would be the hypotenuse of some right triangle that had this line as a leg. And so this line's always going to be shorter. So the projection's always going to be closer to B than sort of any other line in there. So, okay, we've got an inconsistent system. No solution will work. But we say, all right, well, how close can we get? We want the value of X. We'll call it X star, such that we get as close as possible to B. And we realize, okay, well, that means that AX star has to be the projection of B. The projection of B. So now this is our revised goal. Our revised goal in least squares is to find a vector X star such that AX star is the projection of B onto the image of A. And as a side note, an alternative definition of the projection of a vector X onto a subspace V is that the projection is the closest vector to X in V. And in fact, this is actually how I think of projection, especially when dealing in abstract vector spaces where this idea of the casting the shadow doesn't make sense anymore. This is how I think of projection. I also am vaguely regretting that I used X here instead of B. But hopefully, I don't know, you guys are smart enough. You're not confused, right? Well, we're moving on anyway. Okay, so that was the main idea of least squares, what our goal is. Now let's go through and get into some details. So again, our goal is to find a vector X star such that AX star is the projection of B onto the image of A. Our first step is to note that B minus its projection is in the orthogonal complement of the image of A. So this is saying this line right here, this is B minus the projection of B. If you don't believe me, so adding this vector to that vector using arrow, the tip to tail addition gets you B, and then also adding these just algebraically also gets you B. And by the definition of projection, this vector is in the orthogonal complement. So, okay. And now I'm just going to say, well, remember the projection, it's going to be AX star, and we're looking for X star, so let's replace the projection with AX star. So we have B minus AX star is in the orthogonal complement of the image of A. Now, by that first theorem we looked at, this means that B minus AX is in the kernel of A transpose. And what does it mean to be in the kernel? Well, it means that A transpose of the vector B minus AX star, that's going to be 0. All right, well, let's distribute and rearrange. This means that A transpose B is equal to A transpose A times X star. All right. I just want to say, at this point, you're like, all right, well, let's solve for X star. And we can, so long as A transpose A is invertible, we'll just take the inverse and we'll have X star. But when is A transpose A invertible? Well, if the kernel of A is 0, then the kernel of A transpose A is 0 by that theorem that was previously unmotivated. And then if the kernel of A transpose A is 0, then A transpose A is invertible. So consider this retroactive justification for that other unmotivated theorem. Okay, so in that case, if the kernel of A is 0, then we can say that X star, we can solve for it explicitly. It's A transpose A inverse A transpose B. And these are all just like B is going to be some vector that's given to you. A and A transpose are vectors that are given to you. And this is just matrix multiplication that honestly you're going to get a computer to do for you. But this is just straightforward computation. So we get this theorem. If the kernel of A of a matrix A is equal to 0, then the possibly inconsistent system, AX equals B, has what's called the least squares solution, X star, and you can compute X star using this formula. Okay. This is this is really the least squares solution is like the close enough solution. I mean, maybe you've heard of this this phrase, like close only works in horseshoes and hand grenades and least squares. Well, this is where that comes from. The and least squares part comes from this. Okay, so let's use this theorem to actually find the least squares solution of a system. Okay, you've got AX equals B. A is this matrix, B is this vector. Well, we know if the kernel of A is 0, then we can solve explicitly for the least squares solution and using this formula. And let's just check. All right, these columns of A are linearly independent, so indeed the kernel of A is going to be 0, and we can solve for X star explicitly. So okay, computing X star, you just like do it. This is A transpose, this is A, it's inverse. You ask a computer to do it because life's too short. Multiply that by A and then B, and you would calculate this solution here. So in one sense, once you have all the data, you're just plugging away. All right, so what do you do if the kernel is not equal to 0? Don't give up. This is the theme of least squares. Don't give up. Close is good enough. So you can still, if you remember, when we did all those series of calculations, we got up to here without assuming anything about the kernel of A. And then we said, well, if the kernel of A is 0, then we can invert this. So we can still get at least this far. And this is called the normal equation. And I don't really know why it's called normal. But we have this theorem, the least squares solution of this possibly inconsistent system, AX equals B. The least squares solutions of this system are the exact solutions of the consistent system, A transpose AX equals A transpose B. And then this system is called the normal equation for AX equals B. And again, I don't know why it's called the normal equation. It just is. And really, the reason why I bring this up is here's an interesting fact you can tell your friends at parties. It turns out that even if you have a unique least squares solutions, like even if the kernel of A is 0, often it's computationally more efficient to just solve the normal equation using row reduction than to like compute the inverse of A transpose A and then solve for X explicitly. Yeah. So, okay, last thought of this section. So recall what we've seen. We've seen that AX, all right, AX star, if that's the projection, then we have X star equals A transpose A inverse A transpose B. And notice that, all right, well, if we just multiply on this right-hand side, if we multiply A on the left of both of these, then that tells us that the projection of B onto the image of A, which is AX star, is just A times A transpose A inverse A transpose A B. And so we have a new way to calculate the matrix of orthogonal projection. So if you have some subspace with bases V1 to Vm, make the matrix A the columns of your basis vectors, or the columns of A are going to be the basis vectors. And then the matrix of orthogonal projection onto V is just, all right, it's this kind of mess of sequence of matrices here. But that's okay. You're never calculating this by hand. Computers are doing it for you. And what's nice is that this works even if the basis vectors you choose aren't orthonormal. So like in theorem 5.3.10, you needed them to be orthonormal to have a nice way of representing orthogonal projection. But here, you don't have to be orthonormal. You just have to have a basis and for your subspace. And then here you go. You automatically have a matrix for the orthogonal projection. Okay. So now let's talk about data fitting, because this is really where least squares shines. Like, this is the reason why people come up with it. All right. So often in science or statistics, you're asked to find either like something like the line of best fit, which you've probably seen a lot, or sometimes you want to find some polynomial of best fit. Maybe you just want to find the quadratic polynomial of best fit, or some exponential of best fit, depending on what your data like distribution looks like. So yeah, you often want to find some like curve of best fit. And so how do you do it? Well, okay, let's start by doing an example that we've already done in this class. We already know how to do it because it'll illustrate how, in a second, it'll illustrate where least squares comes in. So, okay, here's something we could already do. Suppose, and I think, you had a homework problem like this. Find a cubic polynomial that fits the data points 1, 3, minus 113, 2, 1, and minus 233. And what that's really asking is, okay, find some function c0 plus c1t plus c2t squared plus c3t cubed such that f1 is 3, f minus 1 is 13, f2 is 1, and f minus 2 is 33. And so in previous problems like this, you'd set up some system of equations by basically, you plug 1 in for t and set it equal to 3, plug -1 in for t, set it equal to 13, and so forth. And then you've got a system of equations. You've got 4 equations and 4 unknowns, and so you solve it and you get these, you solve for the coefficients. C0, C1, C2, C3 is this. And then you say, all right, there we go. I found my polynomial that fits the data points. Our C0 was 5, our C1 was -4, our C2 was 3, and our C3 was -1. So here we go. This is our polynomial, and it fits these data points exactly. But frequently, data fitting problems actually lead to a linear system with more equations than variables. Like, you have just tons of data points, and maybe you still want to fit it to a degree 3 polynomial, but now you have more than 4 points, and they're scattered all over the place, and no degree 4 polynomial is just going to hit them all. So such a system, is going to usually be inconsistent. And so that will be, compelled to look for the least squares solution. So, okay, let's look at this example. So we want to fit a quadratic function to the 4 data points that are given here. So what that means is we want some function that is, all right, quadratic, so C0 plus C1t plus C2t squared, such that, all right, f of a1 is b1, f of a2 is b2, f of a3 is b3, f of a4 is b4, which, gives you a system like this. Another way to say this is you're trying to find coefficients C0, C1, C2, such that A, C0, C1, C2 equals B, where A is this matrix. These are the columns of the coefficients, and B is this column. And you can check that this system actually is inconsistent. So we can't do it. We can't find a quadratic function that fits all 4 of these points, that goes through all 4 of the points. But don't give up. Remember, close only works in horseshoes, hand grenades, and least squares. So yeah, what we do is we say, all right, well, we can't solve this, but let's find the coefficients C0 star, C1 star, C2 star that gets us closest to fitting these data points as possible. And so we do that. We find the least square solution, and we do it by just plugging away at these values of A and B that we have. Put that into a computer. You get 5, -1, and 3 as the outputs, or as the coefficients. And so our least squares quadratic function is the function 5 minus t plus 3t squared. And so this is going to be our closest quadratic function that that fits these points. And so let's take a moment and pause and say, but what does it mean to say actually that this is the quadratic function that's closest to the to what we want, that's closest to fitting these? Well, this is actually tied up with the question of why is this even called least squares in the first place? So if you have an overdetermined system, it's almost always going to be the case that there's going to be some error between the data and the curve you wish to fit it to. So in linear, finding the line of best fit, say you've got some scatter plot of the data, you have some line that you want to fit to it. Well, no single line is going to be able to hit through all these points. So no matter what line you pick, there's going to be this error. And I'm considering the error to be the distance between the data point you have and the function value at that point. And so, yeah, you have all of these errors. And so the line of best fit is going to be the one that minimizes these errors. And in fact, the least squares line of best fit is the one that minimizes the squares of these errors. And so, yeah, if your curve is a line, you are minimizing the distance. You're minimizing the squares of these errors. And in our case, we had data points and we wanted a quadratic. And so the quadratic function that we got is the one that minimized the square of these distances, the vertical distances between the data points and the function values. And yeah, I just got lazy and I just drew these in, so sue me. Okay, so that's the least squares because we are squaring up the errors and we want the function that has the least squares of errors. Okay. So, actual final thought. Read the other data fitting examples carefully in your textbook. One of them even kind of tries to explain how least squares really is minimizing those errors that I was just talking about. And really, least squares and data fitting, this is seriously one of the most widely applied ideas that we will see in this class. So really, read the other examples very carefully. All right, I will see you in class.